Hi everyone and welcome to video number 4. Today we're going to be covering another portion of trigonometry. We're going to be doing the T formula, which is going to be very helpful in your knowledge of trigonometry. So today we're going to be learning this important formula, and we're going to learn it from the very core, from the background of it, and we're going to understand how to derive it until we're going to learn its applications. Alright, without wasting time, let's get into today's video. Alright, so next we're going to look at the T formula. So this is going to be one of those formulas that's going to make our work with different equations easier. But before we do that, let's first learn how to derive the T formula. Let's learn where it comes from. Okay, so in some numbers, introducing the parameter t is equal to tan a or t is equal to tan a over 2 turns out to be a very useful tool in solving certain types of trigonometric functions. We express double angles in terms of t is equal to tan a and half angles in terms of t is equal to tan a over 2. So the T formula for sine 2a. So let's look at the sine 2a. So we're going to express, so what happens is the way we get T formula is we have to express all our double angles and make sure that they have a tan inside. So we're going to find a way of expressing. So how do we express this sine, these values here into tan? So the simplest way is we're going to try, remember that that tan comes from dividing a sine a over a cos a. So how do we do that? So we're going to change this a little bit. So we're going to express it like this. So 2 sine a cos a can be expressed as 2 sine a cos squared a over cos a. Now the reason this works is we want to divide this sine a by a cos a, but the only way we can introduce that cos a is by introducing a power here, so that this and this can cancel and it will easily go back to the original. So we now have this. So we know now that sine a over cos a is tan a. So we now have 2 tan a over cos squared a. Now there is a way of expressing a cos squared a in terms of tan, but first it must first be expressed as sec. We know that cos squared a is equal to 1 over sec squared a. So we can have 2 tan a being equal to that. So let's first look at our formulas. So remember that from our formulas we actually have 1 plus tan squared a being equal to sec squared a. So we can express it in that format. So we can express this as 1 plus tan squared a. So we can have it like that. So we now have 2 tan a over 1 plus tan squared a. But remember that since we're looking at double angles here, we can now change them into a t. The t will represent the tan a. So where there is tan a, we change that into a t. So we'll have, for double angles t is equal to tan a, we'll have sine 2a is equal to 2t over 1 plus t squared. So that's the T formula for sine 2a. Alright, how about for the cos 2a? So cos 2a, we remember, is cos squared a minus sine squared a. So one of the first steps we're going to do is, the first thing we're going to do is, let's imagine we have the cos squared a minus sine squared a dividing 1. Okay, so this is how this one is done. And remember what 1 represents. 1 represents cos squared a plus sine squared a. Then we have something like that. So next we're going to divide throughout by cos squared a, and then we'll actually have an expression like so. So we're going to have divide numerator and denominator by cos squared a. Then we'll actually have that. So we divide everything by cos squared a. This will become 1, 1. This will become tan squared a. This will become tan squared a. So we end up with an expression like that. But remember that for double angles, t is tan a. So we'll actually end up with cos 2a being 1 minus t squared over 1 plus t squared. So that is going to be an important formula to memorize. So how about the T formula for the tan 2a? Now the tan 2a is already expressed in terms of tans, so we'll just substitute a t. So for double angles, t is tan a, we'll actually end up with something like that. The tan 2a is 2t over 1 minus t squared. Alright, so next let's look at the T formula for some half angles. So the half angle sine a, we know that sine a is equal to that. So we can also force that to become a t by dividing everything by cos a. and then we'll actually power that. So remember that sine a over 2 divided by cos a over 2 will be tan a over 2, and then remember this value here is the inverse of sec squared, so I have 1 over sec squared a over 2. Then this can be in term change to 1 plus tan squared a over 2. So end up with something like that. So actually realize that for half angles, we'll actually realize that the sine a will also be 2t over 1 plus t squared. So what happens is, for both double angles and for half angles, the t formulas are actually identical. The difference is that for half angles, the t means tan a over 2, and that for double angles, the t means tan a. Okay, so we actually have sine a as being 2t over 1 plus t squared, which is exactly identical as the t formula for sine 2a, but the difference is the t's mean something different. Alright, how about the t formula for cos a? We know that cos a is equal to that, so the same steps, we're going to divide this by 1, and you know that 1 represents cos squared a over 2 plus sine squared a over 2, and then we can divide both numerator and denominator by cos squared a, then we end up with something like that. So half angles, for half angles, t is equal to tan a over 2, and then we have cos a as being 1 minus t squared over 1 plus t squared, of which here the t means tan a over 2. Okay, so that's it for the half angles. So now when you look at the t formula for tan a, which is the half angle, so we know that it's actually already expressed in a format where we actually have a tan a over 2. So just substitute in the t values, and then we'll have that. Alright, so this will make more sense as we look at different numbers. So let's look at this question here. We've been given a question: solve the equation 2 cos theta plus 3 sin theta minus 2 is equal to 0 for values of theta from 0 to 360 degrees. Now, how do we know that a number requires a t formula? It's simple. We can actually see that there is no way of expressing a cos theta to become a sin theta, unless if it was maybe squared. There could have used one of the Pythagorean identities. So here there is no way of changing a cos theta into a sin theta, and also we can also not change the sin theta into a cos theta. There is no direct way, because unless the sine was squared, or maybe it was a double angle or something. So such an example needs t formula. So what do? We're just going to substitute in the different half angles for this. So we now have two different half angles here. So cos theta is a half angle, and then sin theta is also a half angle. So let's look at some of the formulas that we'd actually derived. So remember that for the different half angles, actually remember that the half angles were actually the same as those in the double. The difference was the t's meant different things. So let's actually just go back into our former one. So remember that cos a is 1 minus t squared into 1 plus t squared, of which for the example that we're doing right now, the a, instead of a we have theta, but it's exactly the same thing. And then we also have the sine a or sine theta being as 2t over 1 plus t squared. So those are going to be important to memorize, and they'll be useful. So just going to substitute in the t formula. So for this example, the solution is, let's first write that. So where there is cos theta, we're going to replace that with 1 minus t squared, and then 1 plus t squared. And then where there is the 3, we're going to replace that with 2t over 1 plus t squared, of which the t here means the t, since we're dealing with half angles, the t represents tan theta over 2. So it's now not a over 2, it's now tan theta over 2. Then we're going to simplify these by opening brackets and finding LCM. So when we open brackets, we end up with something like that. Then we find right, so there we go. So then we find the LCM at the bottom. So the LCM is the same. We just open brackets, and then since the denominators are the same, we'll just keep the LCM is exactly identical. Then these numerators just add up each other. Then we're going to cross multiply. Then in cross multiply we have 2 plus t squared. Then we have this on the other side. Then so when we simplify and collect like terms, so 2t minus 2t, these cancel, then the 2's also cancel, then remain with 6t is equal to 0. And then when we divide both sides by 6, we end up with t being equal to 0. So for half angles, which is what we're dealing with here, we remember that the t means tan theta over 2. And then for this example we have, so once substituting where there is 2, we put tan theta over 2. That means this is equal to 0. And then we remain with theta over 2 is tan inverse of 0. So what do we get by tan inverse of 0? Remember, tan inverse of 0 is actually 0. Yes, tan inverse of 0 is 0. So alright, so we're going to have a 0 in the region where tan is positive. So tan is positive here and here. So we actually have a 0 here. So the 0 is exactly on this horizontal line. Then we also have a 0 in this region. So but since we start counting from the horizontal line, that means we actually have it there. So looking at regions of 0 to 360, so our first value is 0 itself, and then the next value is going to be 180. Okay, and yeah, so those are going to be the different values. Now we could have rotated again and found the value of 360, but remember that in our case we're going to be multiplying everything by 2. So we're going to end up with something like theta over 2 being equal to the values that we've actually gotten. Now since we're going to multiply everything by 2, it would not be wise to include the third rotation where we actually have 360, because 360 times 2 is 720, and that is beyond the range. So we end up with theta being, so 2 times 0 is 0 and 2 times 180 is 360. So we end up with values of theta 0 and 360 degrees. So that's going to be it for the first example. Alright, so we're going to look at a UNEB question. This is UNEB 2000 number 2. So we also have two half angles right here, and this is also going to be as easy as the first one. So we're also going to look at half angles where t is equal to tan theta over 2. So wherever there is a theta, wherever there is cos, we're going to replace that with 1 minus t squared over 1 plus t squared. And where there is sin theta, we're going to replace that with 2t over 1 plus t squared. Okay, so there we go. So we actually have that. So we actually just substitute in the values, then we're going to solve. We're going to get the LCM here, and we end up with something like that. So the LCM is 1 plus t squared, which cross multiplies with this. Then we'll actually have 2 plus t squared, and when you collect like terms, we'll end up with 3t squared minus that plus 1 is equal to 0. So when we solve this quadratically, you can actually see that using bulldozer method, we actually remain with t being equal to root 3 over 3. So that's the value of t that I actually get. And now remember that t in half angles means tan theta over 2. So we have tan theta over 2 being equal to root 3 over 3. And then that means tan inverse of root 3. So theta over 2 is tan inverse of that. So the answer we get, we put in our diagram in regions where tan is positive. So tan is positive here and here. So the angle we get is 30. So we're going to place that 30 in regions where tan is positive. So we have it here and here. So our first rotation is that. And now we could also get our second rotation. Now our second rotation is 180. So we actually have 180 plus 30, which is 210. But remember, we're going to be multiplying by 2. Okay. So we would actually have gotten values of 30 and 210. But since we're going to be multiplying by 2, it means this will actually be out of range, because 2 times 210 is 420. So only remain with the answer here. 2 times 30 is 60, of where that 60 is the only one that remains relevant for this number. Alright, so that's the answer. Okay, let's look at the next question. So we've been asked to show that tan 4 theta is equal to that, where t is tan theta. So this is an example of a double angle. Actually, it's a double one, where we've been asked to prove that it's equal to that. So what do we do? So the first step we're going to do is to split this into two different angles. So 4 theta is the same as 2 theta plus 2 theta. So from the left hand side, we can see that tan 4 theta is tan 2 theta plus 2 theta. Then we'll actually have it that now we know that when we express this, we'll actually end up with that. Okay, but we also know that tan 2 theta is the same as we also know that from t formula we know how to express the tan 2 theta. The tan 2 theta is equal to 2t over 1 minus t squared. So we're going to substitute in the t formula into this. Okay, then we'll end up with something like that. So wherever there is tan 2 theta, we'll put this formula right here. So we end up with something like that. So at the top, we're going to find the LCM and also going to find the, so here the brackets open. So end up with something like that. So the LCM at the top is 1 minus t squared. Then these two values add to give us 40. And then here at the bottom, so this times this is 1 minus t squared bracket squared. Then that's going to be the LCM for both of these. Then we'll end up with something like that. And then when we divide this, so we actually have this numerator dividing the denominator. And then when we cross multiply, so when we change that into a multiplication sign, we actually say the denominator will go to the top and the numerator will go to the bottom. And then we'll actually see that this will cancel with one value of this, so actually remain with 1 minus t squared at the top at the numerator. So we end up with a value like that. And then down at the bottom we can actually open this bracket, so we end up with something like this. So end up with this right here minus the 40 squared. So end up with t, so negative t squared minus t squared is negative 2t squared, minus 40 squared is negative 6t squared. So end up with something like this, and hence we've actually proved what we wanted. Right, so for example number 4, we're given solve the equation 7 cos 2 theta plus 3 sin 2 theta is equal to 5 for values of theta from 0 to 360 inclusive. Now when someone looks at this example, someone may almost get the idea of maybe changing both of these and simplifying them, but the fact is when this number is actually a number that actually needs t formula, because both sides are actually already in double angle form, so it's not necessary for us to simplify them, so we can actually just use t formula directly. Alright, so remember that for double angles, t represents tan theta. Unlike half angles, in half angles it represents tan theta over 2, but in double angles it represents tan theta. So since we're going to be treating, so since both of these are double angles, we're going to be using t as tan theta. So we have this expression here. So wherever there is cos 2 theta, we shall actually substitute in the formula of t formula. So where there is cos 2 theta, we have 1 minus t squared over 1 plus t squared. And where there is sin 2 theta, we have 2t over 1 plus t squared. So simplifying that by opening the brackets and finding the LCM, we have that. And then we're going to cross multiply, then we'll actually have that value. So after that, we're going to collect like terms. So collecting like terms, we have 5t plus 7t, which is 12t. Then we're also going to have 5 minus 7, which is negative 2. Then we'll actually end up with something like that at the very end. So we actually have that. So next, we're going to simplify this by dividing everything by 2. Then we end up with this quadratic equation. So you can use any formula that you may want. You can use bulldozer or your calculator, but I prefer using my calculator to speed up everything. So I end up with t being 0.73 or t being negative 0.22. But remember that because both of these are double angles, t represents tan theta. So therefore tan theta is equal to 0.73 or tan theta is equal to negative 0.22. So for tan theta is equal to 0.73, we have tan inverse of 0.73, which is 36.1. So we're going to place 36.1 in regions where tan is positive, and that includes this region and this region, so the first and third quadrant. So we're going to have the 36.1 there, and then we're going to do some rotation. So we're going to have our first angle as 36.1, and our second angle is going to be 180 plus 36.1, which is 216. So we have 36.1 and 216.1. So in this example, we get theta directly. So that thus becomes our final answers for when tan theta is 0.73. How about for when tan theta is negative 0.22? Now this is the negative region of tan. So first of all, we get the tan inverse of 0.22, which is 12.4. So I'll place 12.4. I'll get 12.4 degrees, but now I have to place it in regions where tan is negative. Tan is negative in the second quadrant and in the fourth quadrant. So I will have something like this, 12.4 here and 12.4 there. So let's do some rotations. So my first angle is this, then I'm going to do the second revolution, and then I'll have that. So we have the angles 167.6 and then we have 347.6. So therefore the roots of the equation from this are between 0 and 360 are 36.1, 167.6, 216.1 and 347.6. Alright, so next I have some trial questions for you that you can try out to get better T formula. So the questions are using T formula. Solve the following equations giving values of theta from 0 to 360 inclusive. So you can try this out and get better at T formula. Trigonometry. If this video really helped you, feel free to leave a like on the video and feel free to leave a comment to tell me if it was really helpful to you. And then if you're new to this channel, I still remind you to subscribe and then make sure to hit the notification bell so that you get updated every single time I upload a new video. See you all in my next video.